a new recording here. And I'm going to let you copy down this example. Okay, I think it is helpful to copy examples down. This is called a tank problem. All right, and you're going to be seeing some of these. All right, so we're copying this example down, and then we'll discuss the example. I've seen a few of you students in office hours. I've seen your, you know, you had your video on, so I know what a few of you look like, but, you know, I think students are shy about using their webcams, you know. Okay, so now we have, let's look at this example. It's an applied problem. We have a tank that contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. We want to find out how much salt remains in the tank after half an hour. All right, so this problem, we can model the problem with a differential equation. So to come up with a differential equation, certainly we have to make use of the information in the problem. What do you notice? What do you notice about the 25? Hold on, let me this 25 liters per minute, and keep in mind to start the problem right, we need to find a differential equation. The differential equation, well, I want to say this, I kind of want to get to the solution, but if Y were the amount of salt in the tank, we would need to find a differential equation for dy dt. Okay, so in other words, to answer this question, how much salt remains in the tank after half an hour, we need to come up with a solution y that's a function of time. We need to find that solution. But in this problem, what's different about this problem is, compared to the other ones you looked at in 7.3, the earlier ones, is that we don't have a differential equation. So we have to come up with a differential equation based on the information that's given to us. Okay, and they're giving us interesting information. 0.03 brine, which is a salt solution, brine that contains 0.03 kilograms of salt per liter enters the tank at a rate of 25 liters per minute. They're giving us some rates. And we need rates because the differential equation, whatever it is a rate. It's a rate. So let's just get right to the solution here. Okay. And I'll show you how this works. So this is our solution. And what we're going to do is we're going to let y of t be the amount of salt in kilograms after t minutes. Okay. The amount of salt in kilograms after t minutes. Okay, let me just, whoops, sorry. All right, and we're interested in finding a differential equation for dy dt. So the units for this rate are kilograms per minute. So we want to find an expression for the rate at which salt enters the tank per minute. Okay. So I mean, you know, you have this salty brine that's entering the tank, and then the solution is mixed. As this brine comes into the tank, the solution's mixed, and then the solution drains the tank at the same rate. So this dy dt is going to be based on the difference between the rate at which the salt's coming in and the rate at which the salt's going out. Okay. And of course, the solution, you know, the liquid coming into the tank, the rate at which it comes in, you know, when you drain the tank, it has to drain at the same rate, or else the tank will overflow, right? So so that's why, you know, they say the solution is kept thoroughly mixed and drains from the tank at the same rate. The reason you need the same rate is so that the tank doesn't overflow. So, okay, we got to figure out the rate at which salt's coming into the tank. So, of course, it's important that, you know, the brine's coming into the tank, and it's coming in at 0.03 kilograms per liter. Okay, that's the rate at which the brine is entering the tank. But the units for our derivative are kilograms per minute. So what we have to do to determine the rate in is we have to take the concentration here of salt in this brine solution, 0.03 kilograms per liter, and we have to multiply it by the rate at which the brine is entering the tank, at 25 liters per minute. The liters will simplify out, and you're left with 0.75 kilograms per minute. And that's your rate in. So the brine is, or the salt from the brine is entering the tank at 0.75 kilograms per minute. And you notice I include the units in my work here because that helps me make sure that I'm doing the problem the right way. When you do your problems, a problem like this on the next exam, I want you also to include your units. I'll be looking for that. Okay, that's a part of your work. Are there any questions so far? Please let me know if you have any questions. I'll pause for a minute here to see if there are any questions. All right, well then let's proceed on. Now we have to get rate out. So rate out is going to be the rate at which the salt exits the tank is going to be dependent on the amount of salt in our solution. So the rate out is going to be Y sub t kilograms. That's the amount of salt in our solution at some given time t. And we divide that by 5,000 liters because there are 5,000 liters in the tank. 5,000 liters of water in the tank. Well, the tank drains at the same rate as the brine comes in. So we multiply the concentration, Y over 5,000 times 25 liters per minute. And that gets our rate out. Okay, are there any questions on this? All right, so again, you know, the reason the rate out, the reason the concentration is Y of t over 5,000 is when the liquid leaves the tank, the amount of salt is at that time is what Y of t is. We define Y of t to be the amount of salt, and I should, you know, add here the words in the tank. You know, that's the amount of salt in the tank. That's what Y of t is. But the concentration then would be the salt amount divided by 5,000 liters, because that's how big the tank is. Well, this means then that now we can construct our differential equation. The dy dt is rate in minus rate out. My units are correct for the rates. So the rate in is in kilograms per minute. The rate out is in kilograms per minute. So the difference in the rates, the units will be kilograms per minute. Therefore, dy dt will equal 0.75 minus y over 2,000. And we have our differential equation. We have it. And now we need to solve it. Are there any questions up to this point here? All right, well, so of course, how are we going to solve this differential equation? Well, we know there's going to be a fraction involved. You have the y over 200. Okay, so why not just express the entire right-hand side as a fraction? Okay, so we have 0.75 over 1. Common denominator between 1 and 200 is 200. So I'll multiply by 200 over 200 on the first fraction. And that's going to get me then that dy dt equals 150 minus y over 200. And that is a separable differential equation. It's an autonomous differential equation, actually, and it's a separable differential equation as well. Autonomous differential equations are always separable. Okay, so what we'll do, are there any questions so far? All right, well, what we'll do is we will separate the variables. Okay, so if dy dt equals 150 minus y over 200, then 1 over 150 minus y dy would equal 1 over 200 dt. Are there any questions on that step there? How we got here, here to here? Who's feeling good so far? Give me a thumbs up if you're feeling good about the problem. Okay, thank you, John. Thank you, Julia. Thank you, Robin. Thank you, Tyreek. Who feels a little nervous about the problem? Does anybody feel a little nervous? Well, that's good. That's good. All right, Marvelous is a little bit nervous. Well, that's all right, Marvelous. That's why we're doing this problem together. So, okay, we're going to separate the variables. We did that. Now we'll integrate both sides, the left side with respect to y, but if we integrate the left side, we have to integrate the right side. Okay. Now, to integrate this left side, I could probably figure out the antiderivative of that, the integral of 1 over 150 minus y in my head. I could probably do that. But, is there a little thing that can help us, a little, one of your integration techniques that'll help you with that left side? The right side's no problem, but what easy integration technique would be helpful for the left side? Definitely not integration by parts, right? Substitution. That's right, Robin. We're going to do a substitution. What should we let u equal? What should we let u equal? That's right, Marvelous and John, 150 minus y. So we'll do that. We'll do that. We'll let u equals 150 minus y. Then dy is negative du, and we arrive right here. And it's my style to try to integrate everything at one time. Okay, because if I integrate, I factored out the 1 over 200 on the right side. But if I integrated, that integral on the right, I would have to have since it's an indefinite integral, I'd have to have a constant of integration. Okay, and that's something too. Some of you, when you do your work, like on the exam, you'll do an indefinite integral and you'll forget that constant c of integration, and it needs to be there. Okay, all right. So, okay, we know that the antiderivative of 1 over u is the log of the absolute value of u. All right, so we're just gonna do integration here. And remember, ultimately, to answer this question, I need to know what y of t equals. What y of t equals. So I'm not there yet, but I want to solve this equation here. What do I want to solve this equation for? I see a variable u and a variable t. I want to solve the equation for what variable? Who can chat it out for me? That's right, Tyreek, Josiah, and John. Well, John, hey, John picked a letter in the alphabet. It's going to be you. It's going to be you. So, John, you could, I mean, the thing is, solving for C, if I see where John's coming, if it were an initial value problem, so I want to say one thing. We're going to solve for the variable u, but John is correct that later on we are going to have to worry about solving for our constant C. We are going to have to worry about that. We won't worry about it yet, though. So I don't want the negative in front of the log of u, so I'm going to multiply through by -1. And so the log of the absolute value of u will equal -t over 200 minus c1, and minus c1 is now c2. See, I'm gonna call that c2. So now I have the log of the absolute value of u is -t over 200 plus c2. And we want to get the u, the absolute value of u, by itself. So what do we do to remove the log? What do we do to remove the log? You have some experience with this. You had a problem, you know, using L'Hopital's rule, right? Dealing with this. If we don't want the log anymore, how can we remove it? What can we do to both sides of this equation? That's right, John. Exponentiate. And that's what we'll do. We'll exponentiate both sides. Okay. This is called exponentiation. Exponentiation. How many have seen this before? Maybe in their pre-calculus class. Okay, good. John, Naomi, Francesca, thank you. Michael, Robin, excellent. Sachi, thank you. Very good participation. Very good participation. There's nothing better than being here in the class. So I want to mention, you probably can see how many we have. We have 15 students in our class today. Usually we have more. But don't you worry about the students that are not here. You're here, and really, it's best that you're here. And so you just keep attending. Okay. All right. So all right. So now we have the absolute value of u equals, now e to the, you know, how am I getting this step here? Well, if you have e to the a plus b power, that's going to equal e to the a times e to the b. Because the bases are the same, the base e is the same, you add the exponents. So the absolute value of u can be written as e to the -t over 200 times e to the c over 2 power, and e to the c over 2 power, we'll call that C3. We'll call that C3. Again, it's a new constant. So I'm not going to call e to the c over 2 power C2. Got to call it C3. And that's important for your work, you know, in these problems. Your next exam, you know, I'll be expecting to see that kind of work. And so now what we have here is this. The absolute value of u equals c sub 3, that constant, times e to the negative t over 200. But remember, our goal is to solve for y of t. So at this stage, I'm going to go ahead and replace the u with the 150 minus y. Okay, I'm going to replace that, and that brings the y back in. And the absolute value of 150 minus y, in this case, is going to be 150 minus y. Now, why is that? Well, it turns out that, you know, you started out with, in the tank initially, with, hold on here. Initially, you had 20 grams of salt in the tank. And as the brine comes into the tank, you know, that's going to add more salt to the solution. But y will, I want to say this the right way, y will increase from 20, but it's always going to be less than 150. And the reason is, I'll actually show this later on. I can nicely justify that. But well, I can justify it now. You know, the tank has 5,000 liters of water, and over time you're pumping this brine solution in that contains 0.03 kilograms of salt per liter of water. Salt per liter. Okay. You know, over time, this solution is going to resemble a big, you know, tank of brine solution, because you're pumping this brine into it. And if you take the 5,000 liters of water and multiply it by the brine's concentration of 0.03 kilograms per liter, that's going to equal 150 kilograms of salt. So so y is never going to be over 150. Hence, the absolute value of 150 minus y is 150 minus y. So you always need to justify in these applied problems, when you drop the absolute value, you have to have a little note saying why you're doing that. And that's, again, going to be important for work on your next exam. So I'm trying to point some of these things out to you, and, you know, you're present in class too, and I think, you know, I mean, of course, you know, there'll be a recording, but hey, you know, you're present, and I think it's just nice to point these things out. Now, but hold on here. I want to make another comment here. Let me just see one thing here. So really, I have a plus or minus here, but I really don't need that. I really don't need that here, I don't think. Let me just check the work. This problem is one from the textbook, but or is it one? Yeah, it is one from the textbook. Yeah, I don't need a plus or minus there. I've established that, you know, but it's understood that this C3 would have to be a positive constant, of course. So what I'm going to do is I'm going to call C3 now C. So I'm getting towards the end of the problem, and I like to have my final constant be called like K or C or something like that. So 150 minus y is C times e to the negative t over 200. I can solve for y. Y is 150 minus c times e to the negative t over 200 power. But in order to answer the question, you know, the question was how much salt would remain in the tank after half an hour. Well, I have to have a value for that C. And how would we solve for C? What initial condition were we given in the problem about salt? What initial so this is a solution to the differential equation here for sure. It's a solution to the differential equation, but you know, in order to solve for C, we need to have some initial condition. What initial condition do we know? That's right, John. We're starting out with 20 kilograms of salt. So that means that y of 0 equals 20, and therefore, you can solve for C. You can solve for C as you see here. So at time equals 0, you know, you'll have e to the negative 0 over 200 here. That's just e to the 0. That's 1. And you can see then that C is 130, and therefore now you have your answer. Well, you have the solution to the differential equation. Okay. And so, all right. Are there any questions? Okay. All right. So if we want to find out how much salt is in the tank after half an hour, what are we going to substitute in for T? What value do we substitute in for T? That's right, John. We're going to put in 30 because remember our units here. We'll go back to where we started. Y of T is the amount of salt in the tank after T minutes. So we have to convert the half hour into 30 minutes. And if we do that, we're going to get 38.1 kilograms. Okay, so the original amount of salt in the tank was 20 kilograms. Now it's increasing because this brine solution is coming in. And it's important to note here that as T goes to infinity, the limit of our solution, y of T, is going to equal 150 because e to the negative t over 200, that would approach 0, right? That approaches 0 as t goes to infinity. Okay? And that's an obvious one. You don't need to use L'Hopital's rule on that. But of course, on the exam, there were a few questions where you needed to use L'Hopital's rule to formally get your final limit, you know, the couple of those improper integral problems. And certainly some of you maybe got the limit, but you had to justify it with L'Hopital's rule. So, you know, just making that comment. So, you know, you wouldn't have gotten a perfect score, right, if you didn't have the L'Hopital's rule. But you know, I still gave partial credit. So there we go. Are there any questions on this this particular problem? Okay. Okay. All right. So, all right, I want to stop the recording. I want to go to another problem, but I'm going to stop the recording